Hello and welcome to a slow scientific journey, where great questions about the universe are shared gently, allowing your mind to relax. Tonight, we explore a question that seems simple but is surprisingly strange. If Venus is closer to Earth than Mars, why are humans heading toward Mars? Take a moment to notice where you are listening. Perhaps you sit in a quiet room, wrapped in a blanket, under a dark or fading sky. Wherever you are, talking about planets now connects us all under the same sky. Imagine an evening after sunset. The air softens, life slows, and near the horizon shines a point of light. Steady and bright Venus. Thousands of years ago, long before telescopes or rockets, ancient civilizations noticed it, calling it the morning or evening star. It is not a star, but a planet, often closer to Earth than Mars. So why do we focus on Mars? Not Venus. Mars is red, dusty, and has been explored by robots, capturing our imagination as a future human destination. Venus, though closer, is not easier to reach. Distance alone does not determine accessibility. Temperature, pressure, atmosphere, and survival potential matter more. Early astronomy saw Venus as promising, similar in size and mass to Earth. Its orbit receives familiar sunlight, leading people to imagine tropical worlds, oceans, or even life beneath its clouds. Telescopes revealed a smooth, bright white globe reflecting sunlight, hiding its surface in thick clouds once thought to be water vapor. Mars appeared cold, red, and distant, less Earth-like in imagination. But 20th century probes changed our understanding of Venus. Its atmosphere is nearly entirely carbon dioxide, extremely dense, and its surface temperature averages 465 degrees Celsius, 870 degrees Fahrenheit, hot enough to melt lead. Pressure is 92 times Earth's, and clouds contain sulfuric acid. Venus became a warning, not a sister world. Mars, though cold, negative 60 degrees Celsius, with thin atmosphere and radiation risks, is more manageable. Engineers can insulate, heat, and regulate habitats. Extreme heat, pressure, and corrosive clouds on Venus make survival far harder. Human imagination also favors Mars. Observed markings and supposed canals in the 19th century fueled visions of ancient life or civilization. Venus's surface is hidden. No landscape invites speculation. Humans relate to horizons and walkable landscapes more than a deadly acid world. Orbital mechanics add complexity. Venus orbits inside Earth's path, requiring energy reduction to reach it. Landing and surviving are different challenges. Mars rovers operate for years, whereas Venus landers last only minutes to hours. Human exploration demands long-term survival shelters, food, water, energy. Mars offers frozen water usable for fuel and agriculture. Venus offers almost none at the surface. Floating cities in its upper atmosphere remain theoretical. Hence, humans target Mars. Survivability outweighs proximity. Venus remains scientifically important, as its history of runaway greenhouse effect may teach us about Earth's climate evolution. Mars may host human footprints. Venus may serve as a cautionary tale. Between them lies the reason humanity chooses one frontier over the other. Before continuing, pause again. With that bright point of light, Venus watched for millennia, linking us to the past and to the mysteries of the universe. Venus is closer and brighter, yet our gaze is fixed on Mars. This choice reveals something about humanity: what we fear, what we believe we can survive, and the worlds we imagine inhabiting. At first glance, the choice seems simple. Two rocky planets near Earth, both studied for decades, both sending back data. Yet, when considering long-term human presence, Mars emerges as the destination. Venus recedes into a question mark. Not because Venus is less important scientifically. It challenges assumptions, complicates Earth-like comparisons, and demands attention. But for human missions, only one name feels feasible. Before probes, landers, and atmospheric data. The choice was unclear. Venus and Mars both inspired expectations, speculation, and unanswered questions. The guiding question then was feasibility, not proximity. Feasibility involves physics, technology, biology, psychology, and the accumulation of evidence pointing to where efforts are worthwhile. Mars, though hostile, offers compromise: cold, dry, thin atmosphere, strong radiation, all manageable with insulation, shielding, and controlled habitats. Venus, in contrast, overwhelms life's requirements: extreme heat, crushing pressure, corrosive atmosphere. Solving one hazard leaves others pressing. Engineers plan Mars missions on long timescales, rovers climbing, drilling, analyzing, and transmitting data. Astronauts living in pressurized habitats with protective suits. Venus missions compress these timescales to minutes or hours. The surface cannot support long-term presence. Resources are limited. Ambition must focus where survival is possible. Mars offers continuity. Its dried riverbeds, in freeze, water-dependent minerals, and polar caps suggest a world once warmer and wetter, gradually losing conditions recoverable or adaptable. Venus, by contrast, seems irreversibly transformed, perhaps once with oceans, now locked into extreme heat via runaway greenhouse effects. Intervention on Mars feels plausible. On Venus, almost mythical. Gravity matters. Mars, at 38%, Earth's gravity allows familiar movement and adaptation. Venus, at 90% Earth gravity, only has tolerable conditions high in the atmosphere, requiring floating habitats far above the surface, complex beyond terrestrial norms. Launching from Venus is far harder due to dense atmosphere and drag. Mars missions, though risky, remain calculable. Mars captivates human imagination: hills, valleys, plains, pale sky, rust-colored ground. Venus hides beneath thick clouds, abstract and distant. Humans think in images. Mars offers landscapes our minds can grasp. This visual familiarity influences budgets, public interest, and commitment. Mars symbolizes endurance and exploration. Venus symbolizes excess and warning. Distance alone does not dictate choice. Survival, feasibility, and imagination do. Mars gives time to act. Venus removes it. Yet Venus's brilliance continues to draw attention. Its high albedo, proximity, and thick reflective clouds make it the brightest object after the Moon, visible even in city skies. Moving between dawn and dusk, wandering across the sky. Ancient cultures noticed Venus long before instruments, using it for calendars, rituals, and myths. Yet, despite its presence, it never became a target for human plans. Before space exploration, brightness inspired hope and expectation: large, Earth-like, and visible. Venus seemed familiar and visitable. Humans projected dreams onto it, even as reality would later reveal its hazards. In the early 20th century, some scientists speculated about life on Venus. Its thick atmosphere was seen as protection, not danger. Clouds might bring rain, rivers, vegetation, and perhaps an entire ecosystem. Given the limited data, mistaking Venus for an Earth-like world was understandable. Mars, though later more famous, was less inviting than dimmer. Colder, with harsh polar caps, Venus shone steadily, suggesting vitality. Its brightness made it easier to observe, but the surface remained hidden. The clouds were too thick. This created a paradox. Venus was the easiest to see yet least understood. Mars, dimmer, revealed glimpses of surface features, dust storms, polar regions, topography allowing people to imagine its world. Venus offered only light and mystery. This uncertainty persisted until mid-20th century, when spectroscopy and radio astronomy began measuring Venus's temperature. Early results were contradictory. keeping hope alive. Brightness contributed humans instinctively associate light with warmth, comfort, and life. The eventual truth, Venus's reflective clouds trap heat, creating extreme temperatures, was a shock, overturning expectations. Brightness shifted from invitation to warning. Venus became a planet profoundly different from what humans expected, beautiful from afar, yet inhospitable. Mars, by contrast, remained consistent with early impressions: cold, dry, barren, albeit without imagined civilizations. That difference shaped perception. Mars feels accessible, imaginable. Venus, distant and abstract. Exploration decisions are guided not only by data but by human intuition, which favors environments that are difficult yet understandable. Venus, despite its brightness, evokes caution. Timing also matters. Venus appears during sky transitions at dawn or dusk. Mars appears later at night, integrated with the stars, giving a sense of belonging. Cultural associations accumulated: mythology, calendars, rituals. Visibility alone could not guide interplanetary missions. Data later clarified that Venus's brightness reflects an extreme atmosphere, not hospitable conditions. Scientifically, Venus remains valuable. Its uninhabitable state, caused by a runaway greenhouse effect, provides a natural laboratory to study climate processes and learn about Earth's temperate stability. Its brightness now serves as a planetary scale warning. Mars does not give such direct lessons. Its failures are quiet. Its water disappears, its atmosphere thins, and it cools rather than overheats. Brightness influenced early assumptions. Before space probes and landers, Venus seemed familiar, almost comforting, Earth-like in size, mass, and structure. Early astronomers placed Venus alongside Earth as twins. Unlike smaller, lighter Mars or extreme Mercury, without further data, Venus was imagined as Earth with slightly higher temperatures. Limited spectroscopy and telescope observations showed only size, brightness, and mystery enough to project hope. Venus's clouds inspired countless speculations. On Earth, clouds imply water, weather, interrace, and stability conditions for life. Imagining Venus as warm, 88, with shallow seas, marshes, or dense vegetation was reasonable. Science fiction adopted this vision: tropical planets, jungles, vibrant ecosystems. This optimism was logical. Venus and Earth are similar in size, composition, and orbit. Mars, with a thin atmosphere and visible surface, seemed drier and less inviting. Venus's hidden surface allowed hope to persist longer. Unseen problems could be imagined absent. Even with advancing technology, Venus resisted clarity. Radar mapping was limited. Temperature estimates conflicted. Scientific consensus remained elusive. The twin planet image persisted due to lack of definitive disproof. That changed in the mid-20th century. Spacecraft began measuring Venus. Carbon dioxide dominated. Nitrogen present. Oxygen scarce. Water minimal. Surface temperatures were intensely hot and uniform, erasing any potential habitable zones. Venus was not tropical. It was entirely inhospitable. The contrast with Mars was striking. Mars appeared dry and harsh, but reality matched expectations. Venus had betrayed early assumptions, creating shock and redefining planetary science. The explanation: runaway greenhouse effect. Venus may once have had oceans, but proximity to the sun accelerated evaporation. Water vapor trapped heat. Temperatures rose, and UV radiation split water molecules, allowing hydrogen to escape. Without oceans or plate tectonics to absorb carbon dioxide, volcanic emissions accumulated, locking Venus into a dense, scorching, uninhabitable state. Venus became a cautionary tale, not a failed Earth. Its similarity to Earth at the start diverged dramatically over time. For human exploration, Venus ceased to be a candidate: bright, Earth-like, seemingly familiar. yet hostile, a punishing invitation. Mars, barren but predictable, remained manageable. Timing also matters. Venus's window for habitability closed early. Mars retained potential for hundreds of millions of years. A slowly changing planet like Mars is easier for humans to plan for than a world that slides abruptly into extremes. For decades, Venus has kept its secrets. Its clouds remain unbroken, revealing nothing of the surface. This opacity delays certainty, allowing hope, doubt, and speculation to coexist. Humans eventually had to rely on data, not just sight, to understand the planet. The first spacecraft sent to Venus were designed not to see but to measure radio waves, pressure, temperature, and chemical composition signals beyond human senses. These instruments finally overcame the visual barrier and revealed Venus's reality. The first flybys in the late 1950s and early 1960s shocked scientists. Radio data suggested temperatures far higher than expected, hotter than Mercury. Despite Venus being farther from the Sun, repeated measurements confirmed extreme, nearly uniform heat day and night, showing an efficient atmospheric energy circulation. Atmospheric sampling revealed carbon dioxide dominance, scarce oxygen, minimal water, and clouds of sulfuric acid. The once inviting clouds became a heat-trapping chemical shield, reflecting brilliance from a hostile environment. Landing on Venus was equally extreme. Spacecraft faced crushing pressure, corrosive clouds, and temperatures destroying electronics. Soviet landers of the 1960s-70s were designed for short-lived exposure. The first images from the surface revealed scorched plains, yellowish skies, barren rocks, no water, vegetation, or life. The illusions of habitability finally collapsed. Venus was no longer Earth-like. It had undergone catastrophic transformation. Scientists realized that starting similarity does not guarantee similar outcomes. Stability, feedback loops, and early differences dictate planetary fate. Venus became a cautionary example, a natural experiment in runaway greenhouse effects, tipping points, and climate extremity. This discovery reshaped mission priorities. Long-term human presence on Venus's surface became impossible. Research shifted to orbiters, atmospheric probes, and brief-duration landers. Mars, in contrast, became the practical focus rovers with extended lifespans, resource mapping, and preliminary human exploration planning. Reality, not ideology, drove this shift. Venus retained scientific importance. Its extreme environment illustrates climate feedbacks, planetary limits, and lessons for Earth. Yet for exploration, it ceased to be a candidate for familiarity. Mars, though hostile, offers manageable, comprehensible conditions. Venus's hostility is absolute. Its atmosphere, the dominant, overwhelming force. Psychologically, Venus's reflective clouds misled early intuition, appearing hospitable while concealing danger. Mars, open and barren, feels honest. Humanity tends to favor transparent hardship over hidden catastrophe. The revelation redefined closeness. Proximity in space is meaningless without environmental suitability. Venus is near but effectively unreachable. Mars is farther yet attainable. Even now, Venus inspires questions. How long did it take to reach its current state? Were there intermediate phases? Could life have persisted in temperate cloud layers? Its clouds have revealed their meaning, but the planet's value remains transforming from an imagined twin to a cautionary, scientifically rich world. In short, toe on Venus. The sky itself is the danger, not the ground, horizon, or sun's distance, but the atmosphere dominates, an active, overwhelming force controlling the planet. On Earth, we live under air unnoticed. On Venus, the weight of the sky is lethal, inescapable, and total. On Venus, the sky does not recede. Surface pressure is about 92 times that at Earth's sea level, equivalent to standing a kilometer underwater. But with air, this is a continuous, crushing force. Every structure, machine, or material must resist collapse under immense weight. The pressure arises naturally from Venus's thick, dense atmosphere, mostly carbon dioxide. Unlike Earth, compression remains extreme down to the surface. Even if heat were survivable, the human body could not function normally. Lungs, blood chemistry, and senses would fail. Deep-sea pressure suits would struggle, especially with Venus's heat of 465 degrees Celsius, hot enough to melt lead, warp steel, and destroy electronics. Day and night temperatures are uniform. No polar or seasonal refuge exists. Heat and pressure together eliminate nearly all possibility of survival. Lander missions accepted this reality. Soviet Venera landers were built with thick, pressure-resistant compartments and insulation, but operated only minutes or hours. They sent back images of barren plains under a yellow, oppressive sky, no water, vegetation, or life. The crushing sky prevailed. The illusions of habitability finally collapsed. Material performance is affected unpredictably. Metals deform, seals fail, lubricants degrade, electronics short-circuit, and cooling becomes ineffective. On Mars, thin air and cold can be managed, habitats insulated, heat supplied. On Venus, pressure, heat, chemical corrosion, and dynamic winds operate as a unified, relentless system. Venus's atmosphere is dynamic. Superrotation circulates air faster than the planet spins. Winds reach hundreds of kilometers (h), transporting heat and chemicals. Clouds of sulfuric acid continuously attack materials. Even high-altitude habitats face constant chemical assault, requiring careful material choice and maintenance. One failure risks destruction. Venus's danger is systemic pressure amplifies heat. Heat accelerates chemical reactions. Chemistry destroys materials. Winds spread hazards. No single problem can be solved in isolation. Mars's hazards: radiation, cold, dust, thin air are serious but individually addressable. Venus allows no piecemeal approach. This affects both human and robotic missions. Components must be over-engineered. Operational time remains short, often only hours. Still, orbiters and probes continue to gather valuable data. Radar mapping shows volcanoes, vast plains, and evidence of geological activity. Extended study of the surface remains impossible. The oppressive sky dictates all conditions. Psychologically, Venus is overwhelming. On Mars, astronauts can imagine walking, placing instruments, orienting themselves on solid ground. On Venus, pressure crushes sensation, heat dominates, and standing on the surface is almost meaningless. Even floating habitats carry constant awareness of lethal conditions below. One structural failure leads to destruction. Mars allows imagination to coexist with fear. Venus crushes it under inevitability. This difference is crucial for exploration priorities. Feasibility is not only technical but also about what can be sustained, repaired, and adapted over time. Venus is scientifically invaluable, yet for human presence, Mars is the practical choice. Venus resists adaptability, yet remains fascinating. Its extreme conditions make it uniquely valuable for studying planetary extremes, climate modeling, and exoplanet analogues. Many exoplanets resemble Venus more than Earth or Mars, but common does not mean habitable. Venus's crushing sky demonstrates that habitability is fragile. A world can slide into a hostile, stable state. Once thresholds are crossed, extreme conditions persist for billions of years. Mars follows a different path. It loses atmosphere, cools, and becomes silent rather than overwhelming. These differences shape human choices. Venus allows measurement and learning. Mars allows imagining long-term presence. Venus began quietly, with sunlight, water, and balance, forming alongside Earth from the same primordial disk. For a time, it seemed unremarkable, slightly warmer, slightly closer to the sun, but nothing hinted at collapse. The transformation was gradual, driven by feedback. A runaway greenhouse effect transformed Venus closer to the sun. It received more energy, warming oceans slightly. Increased evaporation pumped water vapor, a potent greenhouse gas, into the atmosphere. More heat trapped more water, reinforcing warming, a positive feedback loop. Small initial changes accumulated until oceans could no longer exist stably. Water boiled away, amplifying the greenhouse effect. On Earth, oceans regulate carbon dioxide. CO2 dissolves, reacts with rock, and locks into minerals. Venus lacked this mechanism. CO2 from volcanism accumulated. Hydrogen escaped to space as UV radiation split water molecules. Oxygen reacted or was carried away. Irreversible thresholds were crossed. Carbon dioxide trapped heat. Surface temperatures soared, sterilizing the planet. This runaway greenhouse effect illustrates structural climate change. Feedback loops gain control. Returning to previous states becomes nearly impossible. Venus did not heat intentionally. Physics allowed it. Mars avoided this fate due to weaker gravity, thinner atmosphere, and cooler temperatures. It lost heat instead of overheating, froze water instead of boiling it. Earth occupies a narrow intermediate zone, warm enough for liquid water, cool enough to prevent uncontrolled evaporation, stabilized by magnetic field, plate tectonics, and carbon cycles. Small differences, slightly more sunlight. Minor atmospheric variations accumulated over billions of years, producing radically divergent outcomes. Venus is a real-world example of crossing the runaway greenhouse threshold, critical for climate science and exoplanet studies. Many close-orbiting, Earth-sized exoplanets may undergo similar effects. Earth remains protected, but Venus warns that planetary climates are not guaranteed benign. From an exploration standpoint, Venus's greenhouse effect makes it sustainably hostile, not temporary. Cooling it would require removing vast amounts of CO2 or blocking sunlight planet-wide, far beyond current human capability. Mars, in contrast, presents challenges that, while serious, do not amplify each other. Psychologically, runaway effects matter. Humans tolerate gradual changes, but tipping points where systems respond exponentially cause discomfort. Venus exemplifies such irreversible thresholds, while Mars offers gradual, manageable change. Venus embodies fear, a world past the point of no return, not through a catastrophe but through gradual accumulation. Sunlight, water, atmosphere, and time. Mars feels like slow decline. Venus is permanently overheated. Choosing Mars over Venus is a choice between two planetary futures, loss and thinning versus excess and confinement. Loss can sometimes be reversed. Excess is almost irreversible. This influences exploration strategy. Engineers favor worlds where systems can be adjusted gradually. Mars meets this. Venus does not. Venus's proximity is meaningless. Intervention must contend with an interlocked, resistant climate system. Mars's thin atmosphere and cold surface are workable energy. Pressure and habitats can create stable zones. Venus's stability is extreme, predictable but inaccessible. Venus's climate is consistently hostile, hot, dense, and permanent. Mars, fragile but understandable, allows imagination. Venus became less a destination, more a reference, a cautionary example of runaway feedback loops. It shows why humans favor worlds that can be nudged, not ones that resist all change. Proximity does not equal safety. Similarity does not guarantee familiarity. Venus teaches how not to fall into a planet's fate. Mars presents differently. Dim, quiet, a cold desert next door. It is tangible, a surface to stand upon, though requiring extensive support. Average temperature, 60 degrees Celsius. Equatorial days may rise briefly above freezing. Nights and poles are harsher. Humans recognize cold, having adapted to icy environments on Earth for millennia. Technology, insulation, heating, climate control allows survival. Mars's thin atmosphere, 1% of Earth, can be supplemented in habitats. Oxygen can be supplied. Pressure maintained. The surface is solid, predictable, and supports anchoring structures. Venus's surface, in contrast, is nearly impossible to access for long periods. Mars allows gradual exploration. Rovers drive, climb, drill, and analyze, revealing seasons, dust cycles, and history. Time is available for science. Venus permits only brief interaction. Mars preserves memory. Dry riverbeds, delta-like formations, water-dependent minerals, polar ice caps all indicate it was once warmer, wetter, and capable of sustaining liquid water. Its decline was gradual. Atmosphere thinned, magnetic field weakened, solar wind carried away gases. Venus, repeatedly resurfaced by volcanism, erased most ancient features. Mars retains its past, making it valuable as both destination and repository. Mars offers practical resources. Water ice exists at poles and beneath the surface, usable for drinking, agriculture, oxygen, and rocket fuel via electrolysis. Carbon dioxide in the atmosphere can also be processed into oxygen and fuel. These conditions make Mars credible for long-term planning, credibility being essential. Gravity. 38% of Earth allows movement and orientation. Astronauts can walk, carry equipment, and perform tasks. Low gravity effects are a concern but known. Venus has Earth-like gravity, yet the only habitable region lies high in the atmosphere, fully artificial and detached from a solid surface. Mars integrates gravity and terrain. Light is manageable. Mars receives enough sunlight for solar power. A sol is slightly longer than an Earth day, supporting human biological cycles. Venus rotates extremely slowly, requiring artificial lighting for floating habitats, disconnecting inhabitants from natural rhythms. Mars feels more like home. Mars is honest. What you see: rust-colored plains, cratered highlands, thin sky is real. Failures are understandable. Engineering problems, dust storms, broken wheels, power loss. Venus is inevitable. Failure feels unavoidable. This nurtures long-term ambition. Mars allows repetition, learning, and gradual progress. Each rover builds on its predecessor. Landers advance step by step. Venus demands starting over under the same harsh conditions. Mars sits at the edge of habitability, barren, cold, possibly once life-supporting. It is comprehensible and tangible. Venus feels closed off, inaccessible. Strategically, Mars is far enough for serious commitment, close enough for manageable communication delays. Return missions and emergency planning are feasible. Mars acts as a proving ground for future exploration. Asteroids, moons, distant planets. Venus offers no such environment. Mars is not comfortable. Radiation, dust storms, perchlorates, and thin air pose challenges, but they are addressable. Insulation, shielding, pressurized habitats, underground shelters. Mars allows human effort to succeed. Venus imposes absolute limits, emotionally and imaginatively. Mars provides concrete imagery: boots in dust, pressurized modules, rovers outside research stations. Venus's floating cities remain abstract and intangible. Mars's boundaries can be pushed. Venus's push back harder. Cold versus heat is a crucial difference. Cold can be managed by adding energy or insulation. Heat, especially in an environment already saturated, leaves no escape. Heat must be removed, which is far more difficult. Mars's cold is manageable. The thin atmosphere allows rapid heat radiation, and human, robotic systems only need to retain energy. Venus's heat overwhelms, removing options. In short, Mars allows time, adaptation, learning, and gradual exploration. Venus's extreme heat, pressure, and chemical hostility prevent long-term presence and incremental progress. Cold is harsh but manageable. Heat is absolute and prohibitive. On Earth, humans manage cold every day. Insulation, layered clothing, thermal design for electronics, spacecraft heaters, and reflective coatings. Mars extends this challenge. It is cold, but manageable. Venus redefines it. The problem is not retaining heat, but escaping it. The dense, Hot atmosphere continuously transfers heat to everything, leaving no cold reservoir for dissipation. Electronics, cooling systems, and materials cannot operate effectively. Heat is constant and overwhelming. High pressure amplifies the problem. Dense CO2 conducts heat efficiently. Objects rapidly reach thermal equilibrium with the environment. Insulation only delays inevitable heating. On Mars, thin air slows heat transfer, giving systems time to respond. Waste heat can even be useful. On Venus, heat adds to the extreme conditions, crushing performance. Cold also benefits structural predictability. Materials behave more consistently, allowing for design adjustments. Prolonged heat causes deformation, oxidation, seal failures, and electronics malfunction processes that are continuous on Venus. Mars allows maintenance intervals, Venus does not. The human body illustrates the difference. On Earth, metabolism generates heat. Cold challenges can be mitigated with clothing, shelter, and heating. Hot environments, especially hotter than the body and surrounding air, prevent heat dissipation. Core temperature rises. Enzyme fail. Organs shut down. Venus's surface is immediately lethal. No natural adaptation or cooling suit could cope. Mars's cold is extreme but manageable with technology. Cold becomes an asset. Heat is absolute. Energy generation favors cold. Mars solar panels function. Nuclear sources work. Waste. Heat can warm habitats. Venus surface sunlight is blocked. Thick atmosphere scatters light. Cooling systems must overcome continuous external heat. Cold environments allow intervention. Hot, stable environments resist change. Mars offers openings. Venus enforces locks. Mission philosophy follows this difference. Mars missions aim for longevity. Rovers operate for years. Habitats designed for decades. Failures can be addressed incrementally. Venus missions collect data quickly, accept inevitable failure, and cannot rely on repairs. Time is a resource. Cold buys it. Heat consumes it. Cold aids preservation. Materials, organics, and samples degrade slowly. Heat accelerates chemical reactions, material wear, and data loss. Mars preserves planetary history. Venus erases it. Cold allows humans to leave, return, and iterate. Heat prevents iterative learning. Even floating habitats on Venus's upper atmosphere face chemical corrosion, dynamic instability, and risk of falling to lethal lower layers. On Mars, malfunctions remain dangerous but manageable. Cold allows tolerance and opportunity. Heat imposes constraints. This affects cost, ambition, and public support. Mars enables visible progress. Venus cannot. Most of the universe is cold, so learning to operate in cold, thin atmospheres prepares humans for many destinations. Surviving on Venus mainly prepares for Venus itself. In short, cold is easier than heat, not emotionally, but physically. Cold allows maneuvering, energy management, and iterative learning. Heat constrains all options. Mars sits on the manageable side, challenging, but human tools remain effective. Venus, with its runaway greenhouse and crushing sky, represents extremes where even the best tools struggle. A closer planet is not necessarily the chosen one. Distance matters less than temperature, pressure, and energy flow. Cold, like on Mars, can be managed step by step. Venus's heat is almost absolute, guiding all decisions about long-term human presence. Colonization in practical terms means sustained presence, living without constant Earth resupply, surviving accidents, repairing failures, growing food, recycling air and water, enduring years, not weeks. Mars allows this. Venus does not. Mars lies at the edge of feasibility. It provides just enough compatibility and safety margin for planners to design realistic scenarios. Maintaining a human presence requires air, water, energy, shelter, redundancy, and repair capability. Mars allows these to be created. Venus makes them nearly impossible. Air Mars is thin, CO2 rich atmosphere is unbreathable but a resource. MOXIE demonstrated oxygen production on site. Transporting oxygen from Earth is costly. Producing it locally makes Mars partially self-sufficient. Venus is dense. Hot atmosphere makes such processing extreme, risking equipment failure. Water. Mars has subsurface ice at poles and mixed in regolith. It can be extracted, melted, purified, and recycled. Venus has almost no water. Only trace vapor exists in the upper atmosphere. Extracting usable quantities is impractical. Food. Mars allows controlled agriculture in sealed habitats. Crops need light, water, nutrients, and protection. Regolith can be treated for use. Venus requires completely artificial floating structures, imported soil, perfect water recycling. A single failure can collapse the system. Mars allows experimentation. Venus demands perfection. Energy. Mars receives less sunlight than Earth but sufficient for solar systems. Nuclear power is viable. Waste heat can warm habitats. Venus has abundant sunlight above clouds, but surface energy is almost unusable. Floating habitats still face atmospheric dynamics, chemical corrosion, and risk of descending into lethal layers. Mars is predictable. Venus is precarious. Shelter. Mars can use surface or underground habitats. Regolith or lava tubes provide stable protection from radiation. Humans are accustomed to subterranean living. Venus requires floating habitats, maintaining buoyancy constantly. Structural integrity is threatened by corrosion, turbulence, and material fatigue. The solid ground that exists on Mars does not exist practically on Venus. Repair. Mars allows meaningful maintenance. Materials degrade slowly, tools function, spare parts can be manufactured or 3D printed. On Venus, failures occur quickly. Maintenance is a race against environmental destruction. Time is critical. Colonization is surviving under worst-case conditions: dust storms, power failures, equipment breakdowns, illness, human error. Mars offers safety margins. Venus offers almost none. Cold can be mitigated, heat cannot. Mars allows learning, iteration, and sustained presence. Venus limits everything from the start. There is also a psychological factor. Long-term human presence requires not only physical survival, but mental endurance. People need rhythm, variation, and the sense that effort accumulates rather than resets. Mars provides landscapes, horizons, terrain, and movement. Even in enclosed habitats, knowing the ground exists outside has profound psychological significance. Venus's floating habitats are visually monotonous and isolating. No walks, no exploration. Every habitat is an isolated island above a deadly abyss. Humans can adapt to extremes, but limits exist. Mars allows gradual improvement. Venus only permits endurance. This difference affects serious discussions of colonization. Mars is framed within margins. Venus is framed as an experiment. Terraforming illustrates this clearly. On Mars, hypothetical terraforming, thickening the atmosphere, warming. Adding water moves the planet toward habitability. Venus requires the opposite cooling, removing or sequestering CO2, reflecting sunlight, and destabilizing a long-stabilized climate system. Proposed Venus interventions include massive orbital sunshields, converting CO2 to carbonates, or engineered organisms to transform the atmosphere over centuries. All face a wall of scale. Venus has been in its state for billions of years, with orders of magnitude more CO2 than Earth. Even partially blocking sunlight leaves the atmosphere hot. Cooling would occur over geological timescales. CO2 removal is extremely inefficient in Venus's hot, dry environment. Biological or mechanical approaches remain impractical. Energy requirements approach stellar scales. Every solution generates new problems. Mars, by contrast, only requires enhancement, not total reversal. Small changes can incrementally improve habitability. Venus offers almost no incremental path. any misstep risks destabilizing what is already extreme. Terraforming fantasies often ignore this. Planets are not clay, they are complex, self-reinforcing systems. Mars is energy deficient, Venus is energy saturated. Strengthening a weak greenhouse is easier than dismantling a runaway one. Time also matters. Mars terraforming, if feasible, would take centuries or millennia, a long, incremental path. Venus would take even longer, requiring planetary-scale infrastructure and technology beyond human reach. Mars remains imaginable. Venus is largely speculative. Even if terraforming is possible in theory, many scientists favor localized, enclosed habitats instead of planetary-scale change. Mars can be made locally habitable. Venus cannot. Floating habitats on Venus are adaptations, not terraforming. They carve survival bubbles in a system that remains hostile. Mars allows adaptation and incremental transformation. Venus only allows limited adaptation. This asymmetry explains why discussions of terraforming focus on Mars. Mars offers slopes to climb. Venus erects walls. Incremental changes raising temperature, increasing pressure. Expanding habitable zones are conceivable on Mars. Venus offers all-or-nothing challenges. Ethics also factor in. Altering Mars could erase microbial history. Preserving natural states may be more important than reshaping. Venus's surface is likely sterile, but upper atmosphere microbes, if they exist, could be disrupted by terraforming. Even imagination carries consequences. Mars captures attention because it feels unfinished. Venus is fully formed. Mars invites intervention. Venus resists. Terraforming discussions highlight this contrast. Mars feels like a blank canvas, Venus like a solved equation. Saving Venus implies it is broken, but from its own perspective, it is stable, functioning according to physical laws. Stability itself is the first obstacle. Any attempt to alter Venus confronts extreme resistance. Its atmosphere, temperature, and pressure are locked in. Energy flows reinforce the runaway greenhouse. CO2 dominates structurally. Saving Venus means dismantling an entire process, not nudging it. Proposals focus on reducing solar input orbital sunshields or mirrors to block radiation. In principle, reducing energy input could cool the planet, but the scale is staggering. Shields nearly planet-sized, requiring precise positioning for centuries. Surviving radiation and micrometeoroids, cooling would occur on geological timescales. The thick atmosphere retains enormous thermal energy. Even cooling alone does not solve pressure. CO2 must be removed or chemically sequestered. Converting CO2 to carbonates is inefficient on Venus due to heat and dryness. Engineered organisms face extreme chemical, thermal, and dynamic instability. Mechanical removal of the atmosphere requires energy far beyond human capacity. Splitting CO2 into carbon and oxygen on a planetary scale is theoretically possible, but practically impossible. Energy demands are stellar. Oxygen is reactive and dangerous, and carbon must be stabilized. Every solution introduces new challenges. Venus exemplifies a recurring theme. Every intervention triggers cascading consequences. Its tightly coupled system makes changing one variable almost impossible without affecting others. Mars is more decoupled. Atmosphere thickening or surface warming can be trialed incrementally. Venus offers no such privilege. Floating cities on Venus, though appealing, do not save the planet. At 50 km altitude, temperatures and pressures are Earth-like, inspiring balloon habitat proposals. Humans could survive with protection from acid clouds and strong winds. Solar energy and gravity are manageable, but the atmosphere is dynamic, corrosive, and maintenance-intensive. A single failure could drop a habitat into lethal layers. Scaling is limited. Floating habitats cannot create a self-sustaining planetary ecosystem. This is adaptation, not salvation. Venus's challenge is planetary-wide. The runaway greenhouse cannot be turned off locally. The planet may not need saving. From a cosmic perspective, Venus is stable, obeying physics. Hostility is relative. Venus is only hostile to humans. Altering it imposes human definitions of habitability at immense cost. Time magnifies the challenge. Transforming Venus could take thousands to millions of years. Initiators would never see the outcome. Mars allows small, observable changes over centuries, sustaining human commitment. Venus's salvation is too distant for practical ambition. Framing Venus as broken risks, overlooking its value as a natural laboratory, studying runaway greenhouse effects, tipping points, and climate extremes informs Earth and exoplanet science. Mars invites humans to build. Venus invites reflection. Attempting to save Venus demands not just technology but patience beyond normal human scales. Mars feels unfinished. Venus is fully formed. Mars allows gradual interventions, thickening atmosphere, warming, expanding habitable zones. Venus allows none. Any effort must dismantle an entrenched system. The planet is energy saturated, strengthening a weak greenhouse. Mars is easier than dismantling a runaway one. Venus. The scale of Venus intervention is staggering. Solar shields could reduce incoming energy, but must be planet-sized, precisely maintained for centuries, and survive radiation and micrometeoroids. Cooling would take centuries or millennia. The thick atmosphere stores immense thermal energy. Pressure remains crushing. CO2 removal or sequestration is inefficient. Engineered organisms cannot survive the harsh, acidic, dynamic upper atmosphere. Mechanical or chemical attempts require energy far beyond human capacity. Each solution generates new challenges. Mars only needs enhancement. Venus requires complete reversal. Small miscalculations on Venus could trigger unpredictable feedbacks. Terraforming fantasies often ignore this. Planets are systems, not clay. Mars is energy deficient. Venus is energy saturated. Mars's cold allows maneuvering. Venus's heat constrains it. Time and observation matter. Mars's terraforming could span centuries, allowing multiple human generations to witness progress, sustaining political, economic, and cultural support. Venus's distant timeline is mostly philosophical. Localized habitats are more realistic than planetary-scale intervention. Mars allows controlled, incremental adaptation. Venus allows only fragile, floating survival bubbles. Mars dominates discussion because it offers slopes to climb. Venus erects walls. Ethical concerns exist. Altering Mars could erase microbial history. Venus's surface is likely sterile. Though upper atmosphere microbes may exist, Mars feels unfinished and modifiable. Venus feels complete and extreme. Orbital mechanics further complicate missions. Spacecraft do not travel straight. Paths are curved, dictated by gravity, momentum, and timing. Venus may appear closer, but inward travel toward the Sun requires reducing orbital energy, challenging in practice. Mars requires outward transfer, increasing orbital energy. Both journeys are difficult but stress systems differently. Arrival is another hurdle. Mars's thin atmosphere allows aerobraking spacecraft skim upper layers to reduce speed gradually. Venus's dense atmosphere creates extreme heat and strict constraints for aerobraking. Precision is critical. Margin for error minimal. Landing on Mars involves heat shields, parachutes, powered descent. Venus landers face extreme heat, corrosive chemicals, and immense pressure, stepping into a furnace rather than cold. Fuel production illustrates feasibility. Mars allows in situ resource utilization, splitting water into H2 and O2, processing CO2 into methane and oxygen. Perseverance's MOXIE experiment proved this. Venus's extreme heat and corrosive atmosphere make local fuel production extremely difficult. Chemical processes are unstable. Equipment fails. Operational time short. Return missions. Mars is difficult but achievable. Venus is far more challenging. Launching through dense atmosphere requires enormous thrust and heat-resistant materials. Communication. Mars has delays of minutes to 20+ minutes. Manageable with autonomous systems. Venus is closer, but environmental constraints limit operational time to hours. Once again, time is decisive. Mission planners think in terms of return on investment. A Mars rover can operate for decades. A Venus lander may last only hours. Despite Venus being closer, Mars is closer in usable time. Safety margins also matter. Mars missions benefit from decades of experience. Each builds on the previous. Entry, descent, and landing systems are refined incrementally. Venus offers almost no iteration. Each mission faces the same unchanging, hostile environment. Progress is slower, not from lack of care, but due to extreme conditions. Orbital mechanics further shape missions. Trips to Mars take 6-9 months, posing radiation, muscle loss, and psychological stress, but these are studied on the ISS and long-duration simulations. Venus trips are shorter, but the environment offers no relief, no extended surface stay, no gradual adaptation. Stress is compressed and unforgiving on Venus. Mars allows it to be spread over time. Fuel efficiency relates to payload. Mars missions can carry heavy equipment for long-term operation habitats. Power systems, rovers, instruments. Venus missions require minimal, lightweight, single-use systems. Every kilogram must justify its short operational window. Even gravity assists highlight the difference. Venus often serves as a booster, a waypoint. Mars is a destination. Spacecraft paths are curved, dictated by gravity, momentum, and timing. Venus may seem closer, but reaching it means reducing orbital energy toward the Sun, a complex maneuver. Mars requires increasing energy to climb outward. Both journeys are difficult but stress systems differently. Arrival adds another challenge. Mars's thin atmosphere allows aerobraking, skimming upper layers to slow gradually. Venus's dense atmosphere generates extreme heat. Aerobraking must be precise. Margin for error tiny. Landing Mars landers deal with cold. Venus landers enter a furnace. Fuel production illustrates feasibility. Mars enables in situ resource utilization, splitting water into H2 and O2, processing CO2 into methane and oxygen. Perseverance's MOXIE experiment proved this. Venus's extreme heat and corrosive atmosphere make local fuel production extremely difficult. Chemical processes are unstable. Equipment fails. Operational time brief. Return missions. Mars is difficult but achievable. Venus is far more challenging. Launching through Venus's dense atmosphere demands enormous thrust and heat-resistant materials. Communications. Mars's signal delay minutes to 20+ minutes is manageable. Venus's closer distance offers short delays. But the environment limits operational time to hours again. Time is decisive. Psychologically, humans need not only survival but a sense of progress. Mars provides landscapes, horizons, and terrain for orientation. Even enclosed habitats benefit from the knowledge that the ground exists outside. Venus's floating habitats are monotonous, isolated. No exploration, no gradual expansion. Humans can adapt, but Mars allows gradual improvement. Venus only permits endurance. This difference impacts colonization discussions. Mars fits within margins. Venus feels experimental. Terraforming highlights it. Mars can be thickened, warmed, and made more Earth-like incrementally. Venus requires massive cooling, CO2 removal, and sunlight reduction. Planetary scale interventions that are staggering in scale, time span, and risk. Mars feels unfinished. Venus is fully formed. Mars invite intervention. Venus resists. Safety, progress, and psychological feedback favor Mars. On Mars, effort yields, results insulate, shield, extract water, process air. Each problem connects to a solution. Venus resists mapping efforts. Heat, pressure, and chemistry generate cascading problems. Commitment weakens when the path is unclear. Agency matters. En masse, humans can move habitats, explore, adjust systems, and affect their environment. On Venus, even floating structures offer limited agency, drifting with winds, maintaining altitude, reacting rather than shaping. Stress and danger are more manageable on Mars because humans retain control. Venus erodes it. Isolation feels different. Mars is distant. Earth is a faint point of light. Distance creates purpose. Venus is close. Earth seems present, but the unforgiving environment traps humans. Proximity without safety intensifies pressure. Mars feels like exile with a goal. Venus feels like imprisonment without escape. Hazards also differ in kind. Mars is cold, dusty, thin air, radioactive, extreme but familiar. Venus has crushing pressure, molten heat, acid clouds, inaccessible surfaces, entirely alien. Humans can reason about Mars hazards using experience and ancestral memory. Venus offers no reference points. Images reinforce perception. Mars, photos, even blurry, show terrain, horizons, and pale sunsets humans can imagine standing there. Venus images show yellowed, compressed rocks under oppressive skies. They warn rather than invite. Time and continuity matter. Mars shows a process once warmer and wetter. Losing atmosphere and water, gradually loss, is comprehensible. Venus shows permanent entrapment in an extreme state, excess, not decline. Psychologically, loss suggests repair. Entrapment suggests avoidance. Mars aligns with human problem-solving. Challenges are solvable with preparation. Venus resists such. Mapping every solution generates new issues. Long-duration missions depend on belief that actions matter. Mars sustains that belief. Venus erodes it. Mars allows agency, feedback, and incremental progress. Venus enforces constant failure and stress. Humans adapt better with controllable risk. Mars offers it. Venus does not. In sum, Mars is hostile but understandable. Venus is overwhelming and absolute. Mars lets humans struggle and learn. Venus leaves no room for meaningful intervention. Distance, brightness, or apparent proximity cannot override these environmental, psychological, and logistical realities. Time remains critical. Mars missions proceed slowly. Travel takes months. Surface operations years. Routines form. Mars rotates nearly like Earth, giving astronauts morning, afternoon, evening. Important for psychology. Venus's day is alien, longer than its year. Sun rises and sets at a pace unintuitive to humans. Floating habits must rely entirely on artificial light, disconnecting inhabitants from natural rhythms. Humans can survive without natural cycles, but thrive with them. Mars allows that. Venus does not. Even colors matter. Mars's red tones are harsh, but familiar deserts and red rocks exist on Earth. Venus's thick clouds create murky yellow light, low contrast, almost constant brightness, which induces fatigue and disorientation. Mars conveys change. Venus compresses everything. Psychologically, Mars supports learning, gradual mastery, and competence rather than comfort. Hardship is survivable when skill matters. Venus makes skill feel insufficient. That explains Mars' dominance in storytelling, art, and cultural imagination. Mars is challenge and endurance. Venus, once imagined as jungle, became furnace and avoidance. Language reflects this. We go to Mars, but only study Venus. Exploration balance courage and caution. Mars looks like land, Venus like endless hostile atmosphere. Questions of potential life guide billions in budgets and planning. Humans send machines not only to measure rocks or gas, but to detect subtle biological signals. Mars and Venus are both nearby rocky planets with shared components. For life, positions differ. Mars for past life evidence, Venus for possible present life speculation. Mars's story feels familiar. River valleys, deltas, water-formed minerals suggest it was once warmer, wetter, and potentially habitable. Rovers target these sediments and ancient lake beds to seek chemical fingerprints or organics. Evidence is suggestive but inconclusive. Uncertainty strengthens the search. Mars preserves evidence cold, Dry conditions slow decay. Sediments remain accessible. Venus's surface is extreme too hot, too pressurized, sterilized long ago. Attention has shifted to 50 kilometers altitude, where conditions are less extreme. Sulfuric acid clouds exist, chemically hostile, but theoretically within tolerable ranges for extremophiles. Hypotheses include microbial life in the clouds, renewed by possible phosphine detection. Though debated, search strategies differ. Mars rovers drill, collect, move gradually, iteratively build knowledge. Venus fast, high-stakes sampling via balloons or aerial probes, short operational windows, iteration slow due to hostile environment. Preservation matters. Mars retains chemical traces, sediments, isotopic ratios. Past environments are accessible. Venus may have fragile, possibly active cloud life, if any. Surface life, long gone. Sampling is delicate. Extreme conditions limit repeatability. Mars preserves, Venus transforms. Psychologically, Mars offers patience, faith in discoverable evidence. Venus imposes urgency. Mars's long-term exploration is reinforced by hope of cumulative learning. Venus forces immediate, high-risk decisions. Philosophically, finding life on Mars, even fossilized microbes, would suggest life emerges when conditions allow. Venus life would show adaptation to extreme, suspended environments. Both discoveries are revolutionary, but Mars provides iterative, tangible exploration. Venus offers brief, high-stakes encounters. Venus is not forgotten. Renewed interest includes atmosphere study, orbiters, cloud-penetrating probes, yet mission expectations differ. Venus focus on climate, chemistry, extremes. Life is secondary. Mars life is central. This affects budget, timelines, and public imagination. Life on Mars fits the narrative of a sibling planet diverging from Earth. Venus life is stranger, harder to fit into familiar frameworks. Resource allocation balances probability, reward, and feasibility. Mars high on all three. Venus high reward potential, low feasibility for long-term life search missions. That is why the search still favors Mars. Mars makes us kneel beside ancient rocks and ask what they remember. Venus forces instruments into acid clouds, asking what can survive. Both questions matter, but Mars aligns better with step-by-step, mission-by-mission strategies. As the search for life extends beyond the solar system, lessons from both planets shape interpretation of distant atmospheres. In our neighborhood, Mars remains quieter, persistent, methodical, not because it promises life, but because it allows long-term searching without burning out. When moving to technology and human transport, the question of life still underlies all. Exploration is not just stepping on new ground, it is also asking if that ground once harbored life. But before rockets launch, rovers move, or astronauts board seats, reality quietly dictates feasibility, money, budget. It's Michael. Contracts, schedules, trade-offs all determine what is possible. Mars and Venus are unequal here. Mars missions are expensive rockets. Navigation, entry, landing, surface operations, communications, and mission control. Robotic missions already cost hundreds of millions. Crewed missions multiply that. Life support, radiation shielding, redundancy, training, and long-term support push budgets into levels needing international cooperation. Venus missions are also costly heat-resistant materials, reinforced pressure vessels, corrosion-resistant coatings, electronics capable of extreme temperatures, and descent systems able to survive hostile atmospheres. Yet, the return on investment differs. Mars missions last years. Rovers like Opportunity and Curiosity exceed expectations. Orbiters continue transmitting. The longer missions operate, the more data, discoveries, and reasonable cost per return. Venus landers operate briefly. Even successful missions last hours on the surface. Orbiters may persist, but data return is limited. Cost per hour of information is high. Infrastructure further favors Mars. Orbiters relay data to rovers. Surface missions guide landing site selection. Communications and engineering lessons accumulate. Venus missions remain episodic. Each new lander faces the same hostile baseline. Learning curves flatten. Physics does not change. Risk is another factor. Mars missions carry risk, but mitigation is possible. Systems can be improved incrementally. Venus compresses risk no tolerance for error. Early failures appear more probable, making financial investment look riskier. Governments and agencies must justify spending with clear scientific value, technological progress, and public engagement. Mars provides that presence. Every surface photo, drill core, panoramic view reinforces ongoing exploration. Venus remains distant, with images less continuous and episodic, making public engagement harder. Budget priorities respond to perception. Continuous progress sustains support. Crewed missions amplify differences. Sending humans to Mars is costly, but long-term strategies fuel production. Water and air recycling, food growth, infrastructure allow amortized investment over decades. Venus's surface survival is too brief. Floating atmosphere missions add complexity, altitude control, corrosion resistance, emergency systems. Costs remain high continuously. Mars allows development towards stability. Venus enforces tight constraints. Opportunity cost also matters. Budgets are limited. Funds spent on Venus mean less for Mars. Lunar programs, asteroid research, or exoplanet telescopes. Mars intersects multiple objectives: planetary science, astrobiology, crewed exploration, tech development, international cooperation. Venus's scientific value is high, but its alignment with broader human exploration objectives is narrower. Multi-purpose value strengthens funding resilience. Timing matters. Mars missions align with multi-year cycles. Launch windows are predictable. Infrastructure and data streams are maintained. Teams gain experience continuously. Venus missions are episodic, with long gaps, requiring expertise, rebuilding, and budget spikes. Regularity reduces indirect costs. Tolerance for failure shapes perception. Mars missions can fail but provide lessons. The public accepts setbacks. Venus missions are rarer and extreme. Each failure is scrutinized, potentially stifling investment. Private companies also favor projects with incremental, sustainable benefits. Mars evokes a narrative of sustained progress. Venus does not. This is not to say Venus lacks value. Missions continue. Climate scientists, geologists, and atmospheric physicists view it as essential for understanding planetary evolution. But when budgets tighten, priorities sharpen. Mars, associated with long-term human presence, has a clear advantage. Mission costs are not just hardware, they include sustaining momentum. Mars retains momentum. Each mission feeds the next. Data accumulate. Technology improves gradually. Objectives expand step by step. Venus frequently forces resets its environment, breaks continuity. Even in the public imagination, this difference resonates clearly. People can envision a base on Mars gradually growing. Venus, by contrast, limits imagination to a few isolated floating platforms. Perception shapes policy. Commitment is central. Nations attach to projects promising lasting benefits: scientific, technological, cultural, or economic. Mars offers durability. Venus offers understanding, valuable but less anchorable for budgets. Future technological advances, reusable rockets, faster propulsion, high-temperature materials may narrow the gap, but currently environmental compatibility, psychological tolerance, orbital mechanics, and continuity of science all converge with financial reality. Choosing where to go is not curiosity alone. It is sustaining effort over decades without collapsing under cost pressure. Mars fits this framework, setting aside rockets, budgets, and habitats. Venus becomes more personal, a mirror, not comforting, a reflection difficult to regard too long. Venus is not just another planet, it is a lesson in what happens when equilibriums are lost. Earth follows similar physical rules. Venus demonstrates that climate is active, responsive, amplifying feedback loops, and capable of extreme hostile states. The central lesson: nothing is guaranteed to remain moderate. Earth appears stable because oceans exist and temperatures fluctuate within life-permitting limits. Venus challenges the assumption that any Earth-sized planet in a similar orbit will behave the same, nearly identical in size and composition, orbiting the same star. Venus followed a different climate trajectory, not violating physics, but applying it consistently in a slightly different configuration. Feedback is key. Earth's feedback is largely stabilizing. Higher temperatures slow CO2 accumulation via weathering. Oceans absorb heat. Clouds reflect sunlight. Tectonics cycle carbon. These mechanisms give resilience but not immunity. Venus lacked stabilizers. Water evaporation into the atmosphere intensified the greenhouse effect, creating a self-reinforcing positive feedback loop. Eventually, thresholds were crossed where stabilizing processes could not keep up. Thresholds matter. Venus's climate can behave non-linearly. Small input changes create large outputs once boundaries are crossed. Transition from warm to runaway conditions accelerates, not gradually slopes. This is not speculation. Venus's current state is direct evidence. Permanence is another lesson. Its water loss is irreversible. Hydrogen escaped. Oceans cannot return. Earth retains water via gravity and magnetic field. Venus reminds us that some losses are permanent. Risk perception changes. It is not just magnitude, but whether change pushes a system into a new stable basin. Returning to a previous state may require forces beyond natural or human intervention. Carbon dioxide lessons. Earth has trace CO2 with large effect. Venus's atmosphere is nearly all CO2, showing that abundance is less important than participation in feedback loops. Venus exemplifies extreme endpoints that began subtly. Timescales matter. Human decisions span years to centuries. Planetary systems span thousands to millions of years. Venus transformation occur over long time scales, potentially faster than human geological intuition assumes, but slower than lifespans. Processes slow by human standards can still be rapid geologically. Once acceleration begins, no human-scale intervention can reverse it. Venus teaches humility. For long periods, scientists underestimated its conditions. Data lagged reality. Complex systems behave counterintuitively. Comparative planetology is critical. Earth, Venus, Mars form a natural experiment. Earth's stability seems inevitable without Venus as contrast. Outcomes depend on initial conditions, feedback, and history. Inertia is important. Venus's massive atmosphere retains energy efficiently once heated. It persists. Earth's climate also has inertia, but less extreme. Changes propagate slowly but persist. Reducing input does not instantly restore previous state. Delays obscure cause and effect relationships. Venus illustrates energy balance. Solar input differs slightly from Earth, but the temperature gap arises from retention. Outgoing infrared radiation is trapped. Climate depends not only on input, but on escape. This insight is valuable for infrastructure, ecosystems, and beyond. Appearance can deceive. Venus looks bright, calm, serene. Its beauty masks superrotation, turbulence, aggressive chemistry. Many systems appear stable until they are not. The lesson: attention, not fear. Irreversibility and ethics emerge. If Venus once had oceans or life-supporting conditions, their loss is permanent. Earth is currently unique. Prevention is easier than repair. Venus underscores the importance of stewardship. Comparative studies aid exoplanet classification. Earth-like worlds may be rarer than Venus-like ones. Size and distance are insufficient. atmosphere, feedback, history, matter. Venus helps define what Earth-like truly means. Finally, Venus teaches philosophy. Not every world exists to be our home. Some are meant to be understood. Its value lies in what it reveals, not habitability. Exploration is not always settlement, it is restraint, learning from difference, not erasing it. Venus teaches Earth, by contrast, fragile conditions, narrow margins for habitability. Mars teaches loss. Venus teaches excess. Earth lies between extremes. Recognizing this reframes the question of why go here and not there. We choose which lessons to prioritize, not merely a destination. Mars brings lessons about survival, endurance, and rebuilding from what has degraded. Venus brings lessons about limits, thresholds, and consequences. Both are necessary, but only one naturally aligns with humanity's aspiration to remain. Exploration questions shift from which planet is closer to how does humanity want to advance, not merely outward, but deliberately, cautiously, with awareness that every destination shapes technology, risks, and the narratives of progress. The future of exploration will not be a single path. It will be a network of priorities, each branch drawing resources, attention, and imagination. Mars and Venus will both be part of that future, but their roles differ, becoming increasingly clear over time. Mars is seen as a proving ground, not paradise. Not a backup Earth, but a place where humans can test living beyond their home world without immediately confronting an environment that erases safety margins. The focus shifts from symbolic achievement to operational resilience, staying longer, handling problems in situ, reducing dependence on resupply, and surviving where humans are unsupported but not erased. Early exploration emphasizes firsts: orbit, landing, footprints. Vital milestones prove capability, but capability without continuity fades. Persistence is required. Mars meets that need. Planned missions increasingly emphasize infrastructure, energy systems lasting decades, habitats designed for repair, supply chains using local materials, continuous communication networks. These unglamorous objectives mark a shift from visiting to residing. Venus plays a different role. Focus is on extremes, not human footholds. Missions target orbiters, atmospheric probes, and brief landers. The aim is knowledge, not permanence. Venus refines theory. Mars tests practice. Both are essential but demand different mindsets. Technological advances, propulsion, materials, robotics, AI expand possibilities. Shorter journeys reduce radiation and psychological stress. Autonomous systems reduce reliance on real-time control. Mars benefits by enabling independent rovers and habitats coping with dust, thermal swings, and unexpected failures. Venus requires autonomy for survival, but fundamental limits remain. Heat and pressure cannot be overcome by smarter systems alone. Human presence is not central to all exploration. Robots operate where humans cannot, particularly in Venus's atmosphere. High-altitude balloons, long-duration platforms, and orbiters can monitor continuously without surface exposure, addressing atmospheric dynamics, volcanic activity, and climate evolution. Mars robots supplement humans scouting, testing, gathering data. Exploration becomes collaboration. Mars sits at the intersection of human and machine capability. Venus operates largely without human presence. International cooperation shapes future missions. Multi-decadal planning, shared data, and joint engineering favor long-term goals. Mars supports these with persistent infrastructure, scientific benefit, and symbolic value. Venus remains episodic. Continuity is limited. Commercial interests also align with Mars' reusable systems, surface construction, in situ resources, and long-term operations offer economic pathways. Venus's constraints reduce near-term commercial incentives, making it primarily a target for public science. Ethics arise. Terraforming debates involve planetary protection, biosignature preservation, and moral implications. Mars sits at the heart, altering a potentially microbe-hosting world versus preserving natural records. Venus raises similar questions for hypothetical cloud life. But humans cannot live there. Influence is indirect through instruments. Resilience is another theme. Earth is fragile. Climate change, biodiversity loss, resource depletion. Space is a vantage point. Mars observes decline, lost habitability. Venus observes runaway excess, crossed thresholds. Irreversibly. Both guide understanding of planetary stewardship. Venus refines climate models. Mars illustrates atmospheric loss and magnetic decay. Exploration is not choosing one planet, but dividing roles. Mars tests presence. Venus benchmarks limits. Temporal planning matters. Exploration chains stretch decades. Lunar infrastructure supports Mars missions. Mars experience informs deeper journeys. Venus runs parallel knowledge, informs exoplanet and climate studies. Not settlement. Public perception deepens attachment to Mars photos. Sample return. Visible progress. Venus remains distant, intellectually compelling, emotionally untouchable. Adaptability to uncertainty differs. Mars benefits from gradual revelation. Discoveries open new questions, inviting humans to dig deeper. Venus's characteristics: heat, pressure, runaway greenhouse are largely known. Remaining questions are specialized. Narrative momentum thrives on Mars' unfolding complexity. Venus is a largely solved extreme. In sum, Mars supports persistence, learning, and gradual mastery. Venus supports reflection, theory, and understanding planetary limits. Both are invaluable, but only Mars provides a foundation for long-term, stepwise human exploration, while Venus teaches lessons about systemic boundaries, irreversible change, and the consequences of runaway feedback. As exploration continues, attention will shift beyond Mars and Venus. Moons like Europa and Enceladus, with subsurface oceans, Titan with its complex chemistry, and asteroids with resources, all attract interest. Yet Mars remains central, a bridge between Earth and farther destinations, where humans can learn to operate without immediately facing environments that overwhelm endurance. Venus does not serve as that bridge. This may be Venus's greatest contribution by being clearly unsuitable. It sharpens criteria, creates clarity, and prevents romantic notions from overriding reality. Future exploration will demand restraint, precise target selection, sustainability, and respect for planetary systems. Mars fits cautious ambition. Venus stands as a warning of what happens when systems exceed control. Technological advances, propulsion, materials, robotics, AI will benefit both worlds, but asymmetrically. Mars gains autonomy, enabling long-term rovers and habitats to cope with dust, thermal swings, and failures. Venus requires autonomy simply to survive. Yet heat and pressure limit what technology can accomplish. Exploration no longer centers on humans. Robotic missions extend reach. Venus benefits greatly. High-altitude balloons, atmospheric platforms, and orbiters monitor climate, volcanism, and chemistry without surface exposure. Mars robots support human presence, scouting, testing, and gathering data. Collaboration between humans and machines becomes the model. International cooperation favors Mars. Multi-decade planning, shared data, and infrastructure accumulation. Venus missions, though valuable scientifically, remain episodic, limiting continuity. Commercial incentives also favor Mars in situ resource utilization, construction, long-term operation. Venus's extreme conditions reduce near-term commercial viability. Ethics further shape priorities. Terraforming debates emphasize planetary protection, preserving biosignatures, and moral considerations. Mars is at the center, balancing exploration, settlement, and preservation of past life. Venus raises similar questions for hypothetical cloud life, but humans cannot inhabit the planet directly. Resilience and comparative planetology are central. Earth is fragile, Mars shows gradual loss. Venus shows runaway excess. Both inform stewardship. Mars illustrates decline. Venus illustrates thresholds and irreversible change. Each planet's lessons are complementary. Temporal planning matters. Exploration chains span decades. Venus runs parallel to Mars. Knowledge informs exoplanet studies and climate science rather than settlement. Public perception deepens attachment to Mars. Venus remains intellectually compelling but emotionally distant. Mars benefits from gradual uncertainty. Discoveries open new questions, inviting deeper investigation. Venus's extreme conditions are largely known: high heat, crushing pressure, runaway greenhouse. Remaining uncertainties are specialized. Narrative momentum unfolds more slowly. Mars supports persistence, skill building, and incremental mastery. Venus supports reflection, theory, and understanding limits. Mars allows humans to learn, adapt, and envision a sustainable presence. Venus shows consequences when thresholds are crossed. Feedback dominates, and recovery is impossible. Looking ahead, attention expands beyond these two planets, yet Mars remains central, bridging knowledge and capability. Venus is a mirror, familiar in the sky, intimate in presence, yet uncompromising. It cannot be negotiated. Its equilibrium excludes humans. Mars, by contrast, is unfinished, adaptable, and incomplete, offering opportunity for incremental mastery. Destiny in exploration emerges not from proximity, brightness, or ease, but from alignment with what humans can realistically achieve. Mars aligns with endurance. Venus aligns with warning. Venus is critical after Earth, showing what happens when balance is lost. It offers clarity, not comfort. Mars shows fading without collapse. Venus shows excess. Earth lies between, sustained by balance. Going to Mars is not escape, nor abandonment of Earth, but a lesson in sustaining life where conditions are harsh yet manageable. Mars does not welcome, but allows conditional presence. Venus shows what happens when conditions exceed control. Distance does not dictate fate. Feedback, thresholds, and system dynamics do. Humans' preparation for Mars over Venus reflects maturity, choosing environments where presence can be sustained long enough to learn meaningful lessons. Mars allows continuity. Venus does not. This difference grows as humanity reaches farther. Beyond Mars lie moons with subsurface oceans, tidally locked planets, and atmospheres more extreme than anything experienced directly. Many will resemble Venus: extreme, stable, resistant to intervention. Venus prepares humans for this reality. It marks edges of possibility, showing where life can persist and where intervention is futile. Mars lies within one of those corridors, not generous, not forgiving, but not a dead end. Human exploration has always been about learning to live within limits. Early humans adapted to deserts and tundras slowly, learning rhythms, accepting constraints, and building culture around survival. Mars demands that humility. Venus refuses it. Its environment requires transformation on a scale beyond current human capability. Until that changes, Venus is for study, not settlement. Awe, not proximity. Learning, not living. Venus reassures us. It reminds us the universe is not arranged for human convenience. Near does not mean suitable. Brightness is no invitation. For a species stretching beyond its home, these lessons are vital. They teach discernment, temper ambition, and force hard questions. Why go there? What will we learn? What will we trade? Which limits should remain inviolate? Mars and Venus are close in space but far in what they demand. One requires patience and endurance. The other, understanding and restraint. Both are valuable. Both shape humanity's future differently. As exploration expands, the line between study and settlement sharpens. Some worlds teach by allowing presence, others teach by denying it. Venus teaches Earth how climate can fail. Mars teaches how protective layers can be lost. Earth shows how narrow the path is between these outcomes. Going to Mars is not choosing one planet over another. It is choosing a relationship humans can maintain. Mars allows effort, repair, and learning. Venus allows observation, humility, and caution. Distance is not destiny. Destiny is determined by interaction, whether a place allows humans to remain long enough to change themselves without first changing the planet. Mars allows us to try. Venus teaches us to listen. Perhaps the most important lesson is not which planet to visit, but how to leave with fewer assumptions, respect for larger systems, and awareness that some boundaries are meant to be crossed, others to be observed from just the right distance. Even now, under Earth's sky, Venus may rise or set. Mars may hide among distant stars. The nearer shines brighter, the farther waits quietly. Within this opposition lies the answer, not as a rigid conclusion, but as guidance. Humans choose Mars not because it is farther, but because it grants time. Time to learn, adapt, and understand what kind of explorers we are before another world makes distance the determinant of destiny. Humanity has long looked to the sky with curiosity. Yet the planets that shine most vividly, Venus and Mars, teach us very different lessons. Venus, often called the morning or evening star, dominates the horizon with its brilliance, appearing almost intimately close, steady in rhythm across centuries. Its proximity creates a sense of familiarity. It rises before the workday begins, remains visible as the night falls, and seems almost like a companion in the human temporal cycle. This brightness has misled generations into believing that Venus could be a natural extension of Earth, a nearby world inviting exploration, yet that impression is dangerously deceptive. The planet closest to us in sight is not necessarily closest in terms of possibility. The brilliance of its reflection in the sky is no indicator of accessibility, habitability, or survivability. For decades, scientists speculated about Venus as a potential Earth twin. Its size, mass, and density are remarkably similar to Earth's, and in early observations, its thick clouds concealed any direct evidence of inhospitable conditions. Some imagined oceans beneath the clouds, verdant landscapes, or even life forms adapted to a humid, tropical environment. These projections were logical extensions of Earth-based reasoning, a planet formed from similar materials, orbiting the same sun, might follow a similar evolutionary path. Indeed, the absence of visible surface features allowed optimism to persist. Humanity tends to imagine safety where data cannot yet penetrate, and for a time, Venus offered hope as a second Earth. Mars, with its thin atmosphere and barren surface, seemed harsh, dry, and already revealed as marginally habitable at best. Venus held the promise of hidden abundance. However, this narrative began to collapse once the first space missions approached. Radio wave measurements, atmospheric sampling, and later, lander data revealed a different reality. The surface temperature averages around 465 degrees Celsius, capable of melting lead and warping steel. Atmospheric pressure is crushing roughly 92 times that of Earth at sea level, equivalent to standing beneath nearly a kilometer of ocean. Every square centimeter of the surface bears a weight unimaginable in human experience. The clouds, once thought to conceal life-giving rains, are composed primarily of sulfuric acid droplets, corrosive and hostile, suspended within an atmosphere dominated by carbon dioxide with only trace amounts of oxygen or water vapor. These conditions are uniform, omnipresent, and absolute. No place to hide, no polar refuge, no night that offers relief. The planet's atmosphere behaves as a massive, self-reinforcing thermal machine. Heat and pressure combine, amplifying one another, creating a planetary system that is unyielding and consistent in its hostility. This is where Venus transcends mere physical danger. It is a psychological benchmark. Humans cannot intuitively adapt to conditions that provide no incremental learning. Each mission is confined to a window measured in hours. Each lander and instrument faces near certain destruction under pressures, temperatures, and corrosive conditions that overwhelm even the most advanced engineering solutions. Even floating habitats, theoretically possible at roughly 50 kilometers above the surface, where temperatures and pressures are more manageable, are fragile islands in a hostile sea. Constant maintenance, redundancy, and careful monitoring would be mandatory. Failure would lead to immediate catastrophe. There is no safety margin, no chance for incremental progress. In Venus, adaptation is not a gradual, cumulative process. It is an urgent, high-stakes experiment. Venus's atmosphere itself is instructive. Its super-rotating winds, reaching hundreds of kilometers per hour at high altitudes, demonstrate how energy moves with violent efficiency. The positive feedback loop of heat, pressure, and chemical reactivity traps energy indefinitely, ensuring the planet remains in its extreme state. Any attempt to change one variable triggers cascading effects across the entire system. In this sense, Venus is a living example of planetary thresholds. It embodies the consequences of runaway feedback, showing humanity how a planet can reach equilibrium at a state that is entirely incompatible with life as we know it. The lessons are both profound and unsettling. Proximity does not equal accessibility. Similarity does not equal habitability. And stability can be deadly when it exists at extremes. In contrast, Mars presents an environment harsh but legible. Its thin atmosphere, cold temperatures, and surface radiation are extreme compared to Earth. Yet each challenge can be understood, mitigated, and addressed incrementally. On Mars, cold allows time, insulation, active heating, habitat design, and resource extraction can operate gradually, enabling long-term presence. Its surface, while barren, is physically navigable. Gravity is sufficient to maintain orientation. Dust, ice, and regolith can be worked with, analyzed, and leveraged. Every hazard has a corresponding strategy. Every failure teaches a lesson, and progress can accumulate across decades. This slow accumulation of knowledge and capability is precisely what makes Mars the primary candidate for sustained human presence. Even if the environment remains far from forgiving, ultimately, Venus's proximity and brightness in the sky serve as a warning and a reference. The planet offers no comfort, no incremental approach, no stepwise learning. Its value lies in observation, reflection, and understanding the dynamics of extreme planetary systems. Venus forces humanity to confront limits, thresholds, and the consequences of feedback loops unchecked. It shows what happens when conditions push past the point of recovery, and it instructs caution in interpreting seemingly familiar worlds. From Earth, Venus seems intimate. Up close, it is an immovable teacher, highlighting the fragility of life, the necessity of patience, and the importance of respecting the intrinsic laws of planetary systems. While Venus serves as a cautionary benchmark, Mars functions as the bridge between human ambition and practical possibility. It embodies the intersection of danger, opportunity, and endurance, offering lessons not in absolutes, but in gradual mastery. Unlike Venus, Mars allows humans to approach the unknown with incremental understanding, where effort, adaptation, and perseverance accumulate rather than being immediately erased. One of Mars's most crucial advantages lies in time as a resource. A spacecraft journeying to Mars may take 6 to 9 months, but once on the surface, the environment allows sustained presence. The Martian soul, a day only slightly longer than Earth's, provides a rhythm compatible with human circadian cycles. Astronauts can organize daily routines, synchronize activities with light and shadow, and experience a sense of continuity that is psychologically essential. Unlike Venus, where a day exceeds a year and sunlight must be entirely simulated, Mars offers a temporal framework that enables humans to adapt gradually, develop expertise, and build structures that can endure beyond a single mission window. Mars' surface, although hostile, is physically navigable. Its gravity, about 38% of Earth's, allows movement grounded in reality. Equipment, habitats, and rovers interact predictably with the terrain. The regolith can be excavated, slopes can be traversed, and natural features like craters or ridges can be used strategically. Even extreme temperatures, while potentially lethal, can be mitigated with insulation, active heating systems, and careful scheduling. Cold, in essence, leaves room for human ingenuity. Every problem on Mars: radiation, dust storms, subsurface ice, thin air can be approached step by step, with solutions gradually implemented and refined. Mars's environment is challenging, but each challenge is legible, offering feedback loops that reward careful planning and incremental learning. Water, one of the most critical resources for long-term survival, is accessible on Mars. Radar mapping and lander measurements confirm subsurface ice at polar regions and at lower latitudes. Ice can be melted, purified, and recycled for drinking, agriculture, and oxygen production. It can also be split into hydrogen and oxygen to produce fuel. The presence of carbon dioxide in the thin atmosphere is similarly advantageous. Technologies such as MOXIE aboard the Perseverance rover have demonstrated in situ oxygen production. On Venus, by contrast, water is virtually absent at the surface, existing only as trace vapor in the upper clouds. Accessing it in usable quantities would require enormous energy and highly complex systems. Mars, though resource limited, provides tangible possibilities that align with the constraints of human capability. Energy systems on Mars also benefit from predictability. Solar energy, though weaker than on Earth, remains accessible, especially near the equator, and nuclear energy systems operate efficiently in the cold. Waste heat from generators or habitat systems can be used advantageously to maintain internal temperature. Venus's extreme heat and dense atmosphere reverse these dynamics. Energy management is constrained by the environment itself, forcing cooling strategies to operate against a backdrop that is actively hostile. Psychology plays a critical role in the human experience of Mars. The red, rocky landscape, punctuated by cliffs, dunes, and valleys, provides visual and cognitive reference points. Horizons and surface features allow astronauts to orient themselves and navigate, fostering a sense of agency even in an alien world. Efforts are measurable: build a habitat, enhance insulation, deploy solar arrays, move rovers across terrain, and see tangible results. On Venus, the absence of a habitable surface, uniform oppressive atmosphere, and alien visual palette, murky yellow light, low contrast, acid-laden clouds make spatial perception disorienting. Effort rarely translates into durable impact, creating a psychological environment of futility rather than mastery. The iterative nature of exploration is another strength Mars offers. Rovers, landers, and orbiters can operate sequentially, each mission building on the last. Lessons from a failed landing or a mechanical fault inform subsequent design. Knowledge accumulates, data flows continuously. Scientific objectives expand as confidence in operational capacity grows. Venus missions, by contrast, are constrained by the environment itself. Each failure is nearly terminal, and cumulative progress is inherently limited. Time becomes compressed. Operational windows are measured in hours, not years. Mars also allows humans to imagine long-term presence. Habitats can be designed with repair and resilience in mind, supported by local resources such as water ice and regolith. The concept of terraforming, while still speculative, remains conceivable. Slight warming of the surface, thickening of the atmosphere, and gradual introduction of greenhouse gases could incrementally alter conditions toward greater habitability. Venus's terraforming, by contrast, requires planetary-scale interventions, cooling billions of years of accumulated heat, sequestering atmospheric carbon dioxide, or deploying enormous sunshields. The margin for error is infinitesimal. Mars allows testing, adaptation, and learning, Venus demands perfection from the outset. Even risk and cost management favor Mars. Missions can be designed with redundancy and long operational lifespans. Failures, while serious, can be mitigated, studied, and used to inform the next mission. Venus compresses risk and expense into a narrow window. Each instrument, each probe, operates against relentless conditions that leave almost no room for recovery. For governments, agencies, and commercial entities, Mars offers predictable return on investment in terms of science, infrastructure, and public engagement. Venus offers unique insights, but with operational fragility that challenges consistent investment. Finally, Mars allows humanity to build a story of continuity. Each mission, each discovery, adds a layer to a cumulative narrative, the gradual unraveling of its climatic history, the tracing of ancient riverbeds, the study of polar ice, and the pursuit of microbial fossils. This narrative connects human effort over decades and generations, reinforcing motivation, imagination, and practical learning. Venus, in contrast, is episodic. Missions extract data, but the environment limits the persistence of structures and instruments, making continuous engagement far more difficult. Venus, often called Earth's twin due to its similar size and composition, presents a starkly different narrative. Its apparent familiarity belies a reality so hostile that it challenges human ambition at every level. Unlike Mars, where incremental effort can yield tangible progress, Venus enforces constraints that test the limits of engineering, biology, and human imagination simultaneously. This is not speculation. It is grounded in decades of scientific observation and exploration. The first clue of Venus's hostility came from early radar and spectroscopic observations. Radio emissions detected by Earth-based observatories in the 1950s and 1960s suggested unexpectedly high surface temperatures. Initially interpreted as measurement errors, subsequent flybys confirmed a surface far hotter than Mercury. Despite Venus being nearly twice as distant from the Sun, this was later verified by the Soviet Venera program, which sent landers such as Venera 7 inches 1,970, the first human-made object to transmit data from the surface of another planet. Temperatures measured by Venera landers ranged around 465 degrees Celsius, enough to melt lead, while atmospheric pressure reached approximately 92 bars, equivalent to being nearly 1 kilometer underwater on Earth. These measurements are supported by multiple missions, including Venera 914 and the more recent ESA Venus Express, confirming a stable, dense CO2-dominated atmosphere. This extreme environment is not static in character but dynamically enforced by Venus's runaway greenhouse effect. The planet's thick carbon dioxide atmosphere traps heat efficiently, while sulfuric acid clouds reflect sunlight yet contribute to chemical and thermal dynamics. Scientific studies, such as those compiled in the Venus Climate Model (VCM), demonstrate how even minor deviations in atmospheric composition could exponentially increase surface temperatures, illustrating that Venus's climate is a self-reinforcing system, unlike Earth, where feedback loops such as oceanic CO2 absorption, plate tectonics, and weathering stabilize temperature over millennia. Venus lacks sufficient moderating mechanisms. Once the water vapor feedback accelerated, the planet's oceans boiled away, and hydrogen escaped into space. A process confirmed through ultraviolet spectrometry observations that detected the upper atmosphere hydrogen escape rate. Donahue et al. Itenjo by Basha R. Science. The consequences of this runaway greenhouse effect extend beyond temperature. Pressure, heat, and chemical composition act in concert to create an environment that rapidly destroys conventional materials. Metals corrode, electronics overheat, seals fail. Every human-made object on the surface has a lifetime measured in hours, as shown by Venera 13 and 14, which lasted approximately 127 and 57 minutes, respectively, under full environmental stress. Even the most advanced high-temperature electronics today would struggle to survive long-term, highlighting the unique challenge Venus poses for sustainable operations. The psychological dimension is equally significant. Floating habitats proposed at around 50 kilometers altitude offer conditions somewhat closer to Earth pressure, near 1 bar. Temperatures ranging from 0 to 50 degrees Celsius. However, these zones exist within a chemically corrosive, dynamically unstable atmosphere, dominated by sulfuric acid droplets. Any failure in altitude control, structural integrity, or environmental shielding would result in the habitat being forced into layers of lethal heat and pressure. While such concepts are scientifically plausible and frequently explored in studies like those by NASA Glenn Research Center, they remain far from operational reality. Unlike Mars, where humans can envision expansion across terrain and incremental habitat development, Venus allows observation, but not durable presence. Venus' role in science is, paradoxically, amplified precisely because of its hostility. It acts as a benchmark for planetary extremes. By studying Venus, scientists understand the boundaries of climate stability, the thresholds for runaway greenhouse effects, and the long-term consequences of planetary feedback loops. Missions like Venus Express 2006, 2014, and ongoing proposals like Da Vinci Plus and Veritas aim to map surface features, atmospheric composition, and chemical processes in unprecedented detail. These missions do not prepare humans for settlement, but provide crucial comparative data for understanding Earth's climate and potential exoplanet environments. Phosphine detection, reported in 2020 Greaves et al., Nature Astronomy, although debated, illustrates the ongoing interest in exploring Venus's upper cloud layers for potential microbial life, showing that scientific significance remains high even when habitation is impossible. Moreover, Venus teaches a vital lesson about irreversibility. Once a planet crosses certain thresholds: surface water loss, hydrogen escape, runaway greenhouse, its trajectory is effectively locked. This informs not only planetary science, but also human understanding of Earth's climate risks. It shows that extreme states may appear stable and unchanging for billions of years, with little opportunity for mid-course correction. The comparison to Mars is stark. Mars's atmosphere thinned gradually, water froze or escaped, and surface temperatures declined. Feedback loops on Mars did not amplify beyond repair, whereas Venus's feedback loops maintain a stable but deadly equilibrium. Even orbital mechanics underscore Venus's practical challenges. Sending a spacecraft inward toward the Sun is not inherently simpler than sending one outward to Mars. Venus missions must contend with precise timing, thermal stress during entry, and dense atmospheric aerobraking, where failure margins are narrow. Mars, by contrast, allows atmospheric deceleration without extreme heating, providing a broader margin for mission success. Operational windows on Venus are measured in hours. On Mars, they extend to years, allowing data accumulation, iteration, and long-term planning. Ultimately, Venus is a teacher, not a home. Its value lies in shaping human understanding of planetary systems, climate limits, and the consequences of environmental feedback loops. Its danger is absolute. Its lessons are critical. By contrast, Mars allows humans to experiment, adapt, and persist, offering both practical and psychological pathways to long-term exploration. The two planets occupy complementary roles. Venus sets the boundaries. Mars defines the path forward. Humanity's growing knowledge of both helps delineate what is feasible, what is desirable, and what must be observed before it can ever be attempted. While Venus serves as a cautionary mirror, Mars emerges as the natural proving ground for sustained human presence beyond Earth. Its environmental constraints are formidable but not absolute. Humans can anticipate, plan, and gradually adapt to them. This distinction is both practical and psychological. Mars allows effort to accumulate, lessons to compound, and infrastructure to evolve. Each successful mission builds confidence, not only in technology but also in humanity's ability to operate in alien environments. Mars's thin atmosphere, though unbreathable, contains abundant carbon dioxide, CO2. This is not merely an obstacle, it is an opportunity. In situ resource utilization, ISRU technologies, like NASA's MOXIE experiment aboard Perseverance, have already demonstrated the ability to extract oxygen from Martian CO2. This achievement is proof of principle that the atmosphere itself can provide the foundation for sustaining life, producing breathable air, and even generating rocket propellant locally. Unlike Venus, where the atmosphere is too dense and reactive for straightforward chemical processing, Mars provides a workable medium that humans can manipulate safely within protective habitats. Water availability on Mars further strengthens its candidacy. Subsurface ice at polar regions and within mid-latitude, regolith offers a tangible source for drinking. Agriculture and industrial processes, orbital radar mapping and lander observations confirm the presence of ice-rich terrain, such as the vast layers detected by the Mars Reconnaissance Orbiter's SHARAD radar. Controlled extraction allows water to be melted, purified, and recycled, essential for long-term habitation. Venus, in contrast, lost nearly all surface water during its runaway greenhouse transformation. Its remaining trace water exists only as vapor in hostile cloud layers, making extraction extraordinarily difficult and highly inefficient. Mars's gravity, approximately 38% of Earth's, enables human movement that feels grounded rather than disorienting. Astronauts can walk, operate equipment, and interact with their environment without the constant compensations required in microgravity or buoyant upper atmosphere habitats on Venus. This continuity supports not only physical health, but also the psychological well-being essential for prolonged missions. Humans perceive progress when actions produce visible results. On Mars, insulating a habitat, constructing radiation shielding, or deploying solar arrays leads to direct, observable outcomes. Venus offers no equivalent feedback. Efforts to control the environment are continually challenged by extreme heat, crushing pressure, and chemical aggression. Solar energy, though slightly reduced compared to Earth, remains viable on Mars. Solar panels can function effectively, especially near the equator, supplemented by energy storage systems and, if necessary, small-scale nuclear reactors. Heat management is manageable, cold is predictable, and can be mitigated through insulation and heaters. On Venus, the same abundance of solar energy above the cloud layer cannot be effectively harnessed on the surface. Floating habitats must cope with corrosive chemistry and dynamic winds, creating a situation where operational control is fragile and maintenance intensive. Mars, in essence, allows humans to work with the environment, whereas Venus requires continuous struggle against it. Operational timeframes amplify the contrast. Mars rovers like Opportunity and Curiosity have functioned for decades, transmitting vast datasets that refine our understanding of geology, climate, and potential biosignatures. Each successive mission builds upon the previous one, layering expertise and infrastructure gradually. Venus landers, by contrast, survive only hours on the surface. Even advanced orbiters and atmospheric probes cannot substitute for the iterative, cumulative experience achievable on Mars. The return on investment for human and robotic missions is inherently higher on Mars because survival is achievable long enough to justify the enormous expenditure of effort, resources, and planning. Psychological and cultural factors also favor Mars. Humans require a sense of agency and continuity to endure extended missions. On Mars, astronauts can move, repair, and expand habitats incrementally. They can explore surrounding terrain, gather samples, and witness the results of their actions. Venus, with floating habitats suspended in turbulent acid clouds, offers a fundamentally different experience. Every action is temporary, every intervention is fragile, and every failure carries immediate, catastrophic consequences. Mars allows humans to imagine mastery, even if incremental. Venus forces adaptation to the limits of endurance. The planetary history of Mars complements this advantage. Geological evidence shows Mars once harbored liquid water, with ancient river valleys, lake beds, and deltaic structures preserved in the surface. Minerals like clays and hydrated sulfates provide indirect evidence of long-standing aqueous activity, creating a record accessible to rovers and future human explorers. Venus' surface, repeatedly resurfaced by volcanic activity and eroded by extreme heat and pressure, preserves almost no ancient record. The contrast is stark. Mars allows humanity to study history and act upon it. Venus requires only observation, teaching lessons about limits rather than habitation. Even in mission planning, orbital mechanics and risk tolerance favor Mars. Despite a longer journey, typically 6 to 9 months each way, Mars missions permit gradual adaptation to radiation, muscle deconditioning, and psychological stress, supported by terrestrial simulations on the ISS and Earth analogues. Venus missions, though closer in distance, compress stress into hours of operation, leaving no margin for error. Fuel efficiency, trajectory planning, and surface access all favor Mars when long-term human presence is the objective. Finally, the convergence of economics, public engagement, and technological feasibility solidifies Mars as the practical choice for sustained exploration. Budgetary decisions, international cooperation, and commercial investment are all more easily justified when missions demonstrate cumulative progress. Venus's harsh reality, while scientifically compelling, lacks the continuity and incremental gains that anchor long-term planning. Every hour of operation on Venus's surface costs disproportionately in resources and risk, whereas Mars's environment permits iterative development, learning, and adaptation. In essence, Mars embodies human-scaled ambition, a planet challenging enough to require ingenuity, patience, and resilience, yet forgiving enough to allow effort to compound. Venus embodies planetary reality, a world instructive in its extremity, a laboratory for understanding limits, feedback loops, and irreversible processes. The two planets, side by side, frame humanity's understanding of planetary possibilities. One teaches us how to persist. The other teaches us why persistence is never guaranteed. Mars and Venus together define the duality of human exploration. One, a proving ground for endurance, adaptability, and cumulative effort. The other, a mirror reflecting the extremes of planetary physics, warning of thresholds and irreversible processes. Mars offers a world where humans can step carefully, learn deliberately, and build over time, transforming hardship into mastery. Venus offers a world where humans must observe, respect, and internalize the limits of what is possible, reminding us that not all challenges can be overcome with technology or courage alone. This duality shapes our priorities. Mars guides the practice of exploration logistics, engineering, risk management, and sustainable human presence. Venus guides the philosophy of exploration, humility, awareness of planetary boundaries, and the recognition that some systems are immutable. Together, they teach a lesson that transcends mere space travel. Understanding emerges not just from interaction, but also from restraint. Humans do not need to dominate every world to learn from it. Sometimes, survival is the teacher, and observation is the lesson. In planning future missions, this contrast remains decisive. Mars's tangible risks and achievable rewards align with human psychology, technology, and strategy. The iterative, cumulative nature of work on the red planet allows every rover, lander, and habitat to feed into the next mission, building knowledge and infrastructure step by step. Venus, in contrast, operates as a boundary condition. Its extreme pressures, corrosive atmosphere, and runaway greenhouse state force caution sharpen our models, and refine our understanding of planetary evolution without ever permitting prolonged physical presence. From a scientific perspective, the two planets complement each other. Mars acts as a laboratory for habitability, life detection, and human adaptation, while Venus acts as a laboratory for climate extremes, atmospheric physics, and planetary thresholds. Mars allows questions to be tested through prolonged experimentation. Venus allows questions to be tested through careful measurement and modeling. Together, they form a natural experiment in comparative planetology, showing humanity the spectrum of what can occur even under broadly similar starting conditions. Ultimately, the choice to prioritize Mars over Venus for human settlement is not a dismissal of Venus's value. It is an acknowledgement of alignment. Mars aligns with human capacity, incremental learning, and psychological endurance. Venus aligns with understanding, caution, and the limits of intervention. One allows presence, the other enforces perspective. In that perspective lies wisdom, knowing when to act, when to observe, and when to step back. As we look to the future, this insight carries beyond the solar system. Exoplanets, many of which will resemble Venus more than Earth or Mars, will demand similar discernment. Not every world is a home. Not every bright light in the sky invites approach. Some are lessons to be absorbed at a distance. Mars and Venus together teach humanity to measure ambition against feasibility, curiosity against caution, and effort against consequence. So as you read this, and perhaps glance upward at the night sky, remember the lessons of our closest planetary neighbors. Let Mars inspire action, perseverance, and the steady building of capability. Let Venus inspire reflection, humility, and respect for the thresholds of nature. Both teach, both guide, and both are essential. And to you, dear reader, as humanity continues to reach for the stars, may your curiosity remain insatiable, your judgment wise, and your courage tempered by respect for the worlds you explore. May every step you take, every mission you plan, carry forward not only the tools of science but also the awareness of limits and the humility that comes with understanding. Keep looking up, keep learning, and may your journey among the planets always balance daring with discernment.